Alright guys, welcome to these quick notes on 7.2, which deals with sample proportions. So when we want to estimate a population proportion, like a percentage of orange Reese's Pieces in a giant bin, we take a random sample and we calculate the sample proportion. This statistic is found by just dividing the number of successes, or like the certain color of Reese's Pieces, over the total number of Reese's Pieces. Now, the sampling distribution of this is the distribution of values taken by the sample proportion in all possible samples of the same size from that population. And we've seen that before because we did an example of that in class for 7.1, which deals with like the idea of a sample distribution. The reason why we do this is so that this distribution can show all the possible values, and we're also trying to get this idea of an unbiased estimator. A statistic used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. So when we look for that unbiased estimator, what we're kind of focused on is looking at this sampling distribution, and we're trying to identify what the shape would be. In that case, the shape becomes approximately normal. As our sample size starts to increase, it becomes more and more likely to be normal if p is close to 0.5 or is large. In this case, we also know that if we look at the mean of the sampling distribution, it should be exactly the same as the population proportion. So like if I take the mean of all of my sampling proportions, that value should be close to what's the true proportion of the population. Now, we can also measure it by looking at variability of the sampling distribution. And in this case, when we find out what sigma of the sampling proportion, or p hat, is, like we can take the square root of what the population proportion is, or what we assume it to be, times 1 minus p over n, provided that our 10% condition is met. And we're going to talk about that in a second. Just one thing just to note, as our sample size increases, the spread will decrease, as you guys probably saw when we looked at the mean scores of people that took the AP test. As you get more and more values into your sample, the variability starts to decrease, and we start to zero in even more on what the true value is. Okay, so like in this case, we're looking for 10 conditions, or 2 different conditions. That first one that we're going to focus on is like the 10% condition, and we can use the square root or the standard deviation formula that we talked about, which is this one right here, given that the 10% condition is true. And what that means is that n must be no more than 10% of the total population that we're looking at. And we'll look at an example in which we're going to look at Reese's Pieces in the coming days that kind of show this. We also want to check this large count condition. And the normal distribution is going to be approximately normal only if we expect at least 10 successes and 10 failures. To check this, to determine if the sampling distribution is approximately normal, both of these things need to be true. So like we are looking at the fact that n times p needs to be greater than or equal to 10, and also n times 1 minus p needs to be greater than or equal to 10. We're looking for those conditions to be true. If those conditions are true, then we can find the probability of a certain event happening using normal calculations. So we're going to kind of walk through an example. Let's look at a scenario, a poll of 1,500 freshmen where 35% attend a school within 50 miles at home. We want to find the probability that a sample gives a result within 2 percentage points of that of 35%. Okay? So what we're going to do first when we look at this is we always want to check the large count condition, because if the large count condition is true, then we can also use this normal approximation, or use the normal calculations to find the probability of this specific event is happening. So we took 1,500 times 0.35 and we got 525. We took 1,500 times 0.65 and we found that to be 975. Both of those are greater than 10, so we can use normal calculations to find the probability of this specific event happening. So once we do that, the next thing that we want to do is calculate what our mean is, or our mean of all of p hat. Remember, we said that is the same thing as p, and then we want to find out what the standard deviation is. And we talked about how that's P times 1 minus P over N. So in this case, I do have a normal distribution in which the mean is 0.35 and the standard deviation is approximately 0.012315. So the next thing is then we want to calculate what the z-scores are given these specific percentages. We're doing 2% on either side. So we got 1 to be negative 1.624. On the other side, we got positive 1.624. And then after that, what we want to do is based off what those z-scores are, we can find out what the probability is. And we can do that a couple ways. We can use Table A, or we can use this idea of normal CDF to help find the calculations. This is the lower bound, and this is the upper bound. Switched, sorry guys. And then in this case, we're taking the lower bound, which was negative 1.624, all the way up to 1.624. And when we find that probability, using normal CDF, we get it to be 90%. Now, we could also use this in regards to the difference of two proportions, which we're going to talk about in the coming days. And just so that we have this beginning knowledge, we do check the large count and normal conditions to see if this is true. The mean of the difference of two proportions should be what the true proportion of 1 minus the true proportion of 2 is. And then we can also find what the standard deviation is, or what the spread is, by taking P1 times 1 minus P1 over N1. We will see these in action in the coming days, okay? So hopefully this is helpful. This is just a quick note going over what we're kind of starting in the coming days.